Okay, so thank you very much, everybody, for joining. We're starting the lecture. Thank you. Please, Fabio.
Okay. So yesterday we were doing this calculation of the multiple scattering for high energy particle. So I was assuming that we had an initial particle with momentum EF at the initial part. At an initial longitudinal position xi plus find out it's plus, and so we were interested in calculating what I called SFI, which was this state. At x plus, and here we have this path order exponential of the interaction potential. So we were doing it order by order, and we reached an expression. Let me write an expression for the end, and with the insertions of the field and scattering. And remember, we always had this 2 F plus times the delta function for the plus component, and times, and let me write it first in momentum space. So there are a bunch of integrations with the dx and plus from xi plus with the plus and -1 plus and plus all the way to some next 1 plus and then we have some transverse momentum integrals also. One third minus 1 third, and then we had a bunch of what I call vacuum propagators. E0 1 x plus x plus the momentum plus, and then an insertion of the field A minus and x and plus the transfer of momentum third and minus 1 third. So 9 times and also sorry, Muchas días. It continues like that, a bunch of insertions of the gauge field until, let me just write the last one. One x1 plus, one per minus per times the last propagator. Which goes from x1 plus, I plus, that I per. Okay. So, first couple verification, just as a reminder, this G0 that I'm writing everywhere from plus is just this big factor is e to the minus I p third square divided by p plus plus when we write it in coordinate space, is in the space, sorry. It's just the Fourier transform of that. Is the curve. I always forget the sign convention. Just let me get it right. There's that integration can be done analytically. I'm not going to write it because I'm not going to use that expression anywhere. If I were to be a little bit more formal, I should. We have in coordinate space, I have initial and final positions. In momentum space, I only have one momentum instead of on both ends. But if I were to do the Fourier transform separately on both ends, what will happen is that I will just have a delta function of the moment. So instead of writing a bunch of delta functions, I'm just gonna leave it like that. And remember that we also wrote the integral. Okay. This is this is just a reminder of what we did yesterday. We use this path integral to write the general form for this expression also in terms of path integral. I'll get there in a moment. But before I keep going forward, just one little detail that I didn't stress, I didn't emphasize yesterday. I stressed this field, this A minus, is it's a classical field, so in principle it should commute. But I'm always writing this, paying attention to the right order, and at the end we get path order exponentials and all that because it has a color matrix inside. So really, when I write A minus, what I want to say is A minus A. And in principle, I should specify what is the representation that I'm using for the color matrix. Okay, so remember that there's always a color matrix inside there. Because I was doing this for quarks, then the representation of that color matrix that I've been using here is a fundamental representation. I could do the same exercise for gluons. I should probably be more careful how to do the vertex and show that that everything works out. I'm not going to do it. I will leave it as an exercise because I don't have enough time. But in principle, if you do it for a gluon, also the illicit part is trivial. There are no illicit flips in this approximation, and the only thing that you have to do is to change the representation of the color matrix.
But for the gluon, you have a vertex with 4. You have another.
Yes.
Is that suppressed or?
Yes.
Okay.
It is suppressed. We can look at it later if you want.
Okay.
Okay. So, where was it? Okay, so we use this also to write this. The sum of all to all order here in N, I wrote it like this, like this here, and then let me just try to be careful here. So what we showed yesterday is that this can be written in coordinate space. That's why I'm writing here the Fourier transform on the edges in terms of a path integral. Order exponential of integral plus and minus plus okay, and this thing I call this the medium propagator in coordinate space. Okay.
Have you missed a plus on this second PF or is it the full formula?
What? Why did I wrong that twice? I don't know. I don't know what I was thinking. Sorry about that. Okay. So it's we always get this phase factor, the Fourier transform of the in medium propagator in coordinate space, or just simply the medium propagator in momentum space. It will ask you that notation. Okay. Good. So now the issues that path integrals are hard. This is nice to write in a compact form like this, but sometimes it's not that useful. So what I want to show is it's a derivation of some things that this propagator also satisfies. So maybe I should even erase this. Okay, so now what I want to go back to this one, to this expression that we have here for the end term. Now let's forget about this end. I'm just going to talk about the propagator, okay, and forget about the phase factor that was coming from it. So if we look at what is the propagator, the end, this end term, the term with n field insertions and scatterings, in momentum space. So is what is written starting from here. What I want to argue is that this is equal to the integration from xi plus xn plus xn plus of and then integration of -1 I'm gonna write the first part is the same. That is written above. Now, the rest of it, if you look at it from here, it has the exact same form. So what I'm saying is that I took this integration and this one apart, and then the rest of the integrals with what is written in the second line is exactly the n-1 term. But now it doesn't go all the way to xx plus, it goes to xn plus. and the momentum in that at that point is N-1 per. And then on the other end, it goes all the way to Xi. Okay. So now I have a recursive relation here. Which what it tells me is that the n term is the n-1 term with an extra scattering. It's just you just have to be careful with this where the variables appear here. Okay. So you can this works to all n greater than 1. So you can sum this relation, and if I sum over our line here, what do I get? So the full propagator it's equal to the zero term. I have to be careful and just leave it aside for the moment. Divided with a zero. This zero can highlight this just to avoid confusion. Plus the sum of these terms, and I will argue that this I can write as the integration over, let me just call it y. Say L. Here I have G0 X plot, that goes to the Y plot, and here I'll have minus okay. And now this zero term is precisely the term with no interaction, so it's that vacuum propagator there. So I put the zero here on top to not confuse it because of the same what I had just told you about the extra delta function. So this term actually has a 2 pi square delta of the F minus the I curve times G, now with the zero on the bottom of that's the plus, that's I curve. Okay. So this that recursive relation, I turn it into an integral equation that is like a finger Dyson type equation. which is I don't know, something that you're probably familiar with some this is used regularly in perturbative calculations. So that can be useful to write things like this, because you know that gives you an easy way to expand order by order consistently without having to do the calculation every single time. And also you can write this in differential form. So let me take a derivative with respect to xf plus so what happens when I take the derivative with respect to xf plus? In the first term, it hits this term here, which the dependence on the x plus comes from here. It's going to bring a factor. Is that I get a minus I here per square divided by 2 here plus times and what happens when I hit the second term? When the derivative acts on the second term, there are two places where it can act on this on this upper limit of this integration, and it can also act here. Okay, so let's just write first what happens when it acts here. So what happens is exactly the same as here. It just gives me that extra factor from that space. So I get is plus here have a factor of -5 here per the square on times. And then I have the term where the derivative acts here, and that just means that I get rid of this integral, and everywhere where I have a y plot, now I have an x f plus. I get a integration of the curve. So if I replace, so in this term, if I replace the y plot with an xf plus, that gives me a 1, because remember that it depends, it's a phase that depends on the difference on the plus coordinates. So in that term, this factor disappears. So you get the 19 A minus, now evaluated at X F plus. X F plus. Okay. And now you realize that these two terms can be combined into one, because it's in both of them, I only got this extra phase, but the rest is precisely what is written for the propagator. So I can get rid of this one now. Okay. And that's the differential form of that equation, and we can also play the same game and sort of space, or just straight transform the equation that is there on the top. And let me write then first this type of equation in the integral equation in coordinate space will be I'll make the term here. Plus is no, the is 0 in coordinate space. So this convolution that I had here with the integration over L, now it's now it looks like this triple thing, so. Okay, so what I'm, just let me just say one thing and I'll answer the question. So what we're doing here is the following, we're saying, let me just draw something like this. If my propagator, I draw it like this is equal to the one with no interactions plus having singling out the last. I'm singling out the last one. So it looks like this. Okay. That's what I'm doing in this Schwinger Dyson type equations. So if you do it if you're thinking of this in momentum space, then you have a PI here, a PF here. This one will give you a delta function in momentum space. Now this is PI here. This is L perf. There's an L here, and there's a PF here, and then the momentum flux here. It's the PF minus L. That is the one that appears and in the A field here. But if you look at it in coordinate space, this is xi, this is xl. Here you still have the xi, f, xi. And now what we're saying is that this point is y. And then the propagator, this propagator has to go from xi pair to y pair. The field is already at y pair, and the other propagator also starts at y pair. Okay, now there was a question.
Just looking the first term there on the last expression that you wrote, which is zero, is it the 0 on top? Because we don't.
In coordinate space is the same. The distinction that I made between the putting on top or in the bottom was because I wasn't taking, because the zero in the bottom in the momentum expression that I had, I wasn't taking into account that delta function. But in coordinate space is the same. Okay. And now the differential form of this. The differential form of this is so now in the differential form, this term looks much simpler. No, there's no integration, there's no convolution. But the other term now involves a second derivative in the transfer space. Okay. So yes, and if you go from this line to this line is straightforward. You just know that P is the same as I times the derivative with the transverse coordinate, and convolutions in momentum space become products in coordinate space. And if you want to do the same derivation that we did for this one as taking the derivative of this, you just have to go and look carefully at how this it works in the same way, in the sense that this term is the combination of the derivative acting on this and the derivative acting on this. They combine to give me this, and the other term is the derivative acting on the upper limit. You just have to realize that this G0 satisfies the equation without this term, and that's why I can replace the derivatives with respect to x plus in the zero terms by this term here. Okay, and that's a straightforward calculation, just realizing that the G0 satisfies the differential equation without the interaction. So the conclusion here is that this propagator satisfies. This is a Schrodinger equation in 2 dimensions, with the PF plus playing the role of the mass and an imaginary potential. Okay, that's a big distinction. But otherwise, it has the exact same form. Again, at this level, you have to remember that these are color matrices. There are color matrices hidden everywhere. There's a color matrix here, and this is also a color matrix in total. And I haven't said what is A minus. We have to specify what A minus is, because A minus is the background field, and we know very little about that background field in whatever conditions we want to evaluate this. Okay. But I wanted to do this derivation because this, looking at it from this perspective, sometimes can be more useful than just writing the expression in terms of path integrals, which sometimes we don't really know what to do with them. Okay. Any questions up to here? Okay, so now that we know how to resolve those interactions, we have to go back to the original problem that we had, which was figuring out what happens when I have a low emission where I have a scattering all over the place. So we'll have a lot of time, so I'm going to skip over a lot of the details and try to focus on the things that I think need a little more detail in the explanation. So first of all, what is as you can imagine, in principle, what we're going to do is to put in all these parts, just use this propagator that we derive, either here for this line or for this line here. And also for the gluon. But then we have to describe this, we have to do something with this vertex, okay? So Guillaume already did that vertex in his vectors. So let me start putting some. Okay, so from now on, I will stop drawing these lines, and I will just assume that I have them all the time, okay? And that every single line that every one of these lines that I write is it's an in-medium propagator, okay? In general, I will have I'll define here momentum P perp that has some energy E. And emitter gluon with K perp. Oh, let me just keep the plus. P plus, A plus, and this one is Q perp with a Q plus. Okay. So this vertex, Guillaume calculated the other day. All that I care is that I mean, I'm going to call it capital V. Do not confuse with the potential. I'm sorry for repeating notation. I'm not going to do it again. All that I care is that this vertex has depends on the numerical variables. It depends only on the combination. This is 1 minus C times A perp minus Z. Okay, so let me just maybe I should explain that. So what Guillaume actually what Guillaume proved is that if you consider this V as a function of A perp and Q perp, then what he showed is that this is proportional to something. I should probably say what it seems. Z is A plus divided by P. So what Guillaume showed is that the dependence on the transfer momentum variable was always like this. Am I right? This is what you said. Which of course is just what I can write and also remember that there's a delta of P plus minus A plus. So I can write here we have a Q plus over P plus, which is a 1 minus A perp. And here we have a K plus divided by P plus, which is NC. Okay. So that's important that the vertex not only is a function of that, but it's linear in that variable. And okay, so we have in principle, we could have that vertex factor, propagators in all these, propagators here that go from, I have some interaction point, let me call it Y. Maybe a little bit more consistent. This will give me a propagator that goes from X1 with a P1 curve from X initial, let me call it X0 with a P0 with a P plus. This should be a fundamental representation. This also fundamental representation. Now it goes from spinal point, let me call it some X2 plus U curve X1 plus this Q1 curve. And this one will give me a propagator, but a not joint propagator. Okay. Now, if I do everything like that and I keep and I try to calculate what is this amplitude, that's the general case, and it will give me the amplitude for the double differential process. I'm keeping K, I'm keeping Q. Exactly.
And
so
in this diagram, so is you be shifting the moment of compared to
yes.
out of the diagram.
Yes. So I should put ones here everywhere. You're right. My mistake. Okay. So if you were going to do this, you will have like the full double differential amplitude, both in K and Q. That's complicated. You will see later why it becomes very complicated. It has something to the problem is that when you square these, you start having lots and lots of propagators. And at some point, you have to do something with the background field. We will get to that in a minute. And that means calculating lots of averages and averages of several propagators, and that becomes very complicated. So we take a simplification, and that simplification is the following: is saying, okay, in the original case, when at the beginning I was always drawing things like this is a straight line and it radiates some stuff, but I'm assuming that somehow I can follow this particle. There's like one hard particle that is radiating stuff. And that assumption makes that kind of picture makes sense only if the radiation is much softer than if the balloon is much softer than the white, right? Which means that I'll be taking this and this fraction of the plus components. I'll be taking it to be very small. So we're interested in C very small. Now, to make it even easier, what I really want to do is to make the energy of this one so high that I can take that one as iconal. That's completely iconal. It doesn't move in transverse space. And that is something that I do. So it's is something that is going to simplify my calculation a lot. So that's that's going to be your starting point. Then you can see how you can relax that. But in that case, what I want to do is take these propagators, and I know that the limit is something that we wrote yesterday. That limit of the on our trying things like this is except in terms of if I write it in terms of coordinate space. And I take the limit when PF plus is very large, this becomes delta function of the transverse coordinates times a Wilson line evaluated that transverse coordinate, where this U is just this is just the path order exponential and G integration and minus that fixed transfer coordinate. Okay. So I want to use that simplifying assumption for the quark. Okay. And now, so that means that really what I want to do is not only to take the C very small. What I really want to do is to take the simultaneous limit of PF plus. I'm going to, well, in this case, I call it P, only P plus the original momentum going to infinity at the same time that Z goes to 0 in such a way that A plus is equal to E times B plus, where it is final. Okay. That is what we understand for the soft limit in medium induced emissions. So if I do that, then what I get is that this K plus, which is 1 minus Z times P plus, is practically the same as P plus. Okay. So the idea to do these calculations, so it's a little bit contradictory in the sense that the idea of these calculations is to see the energy loss of this initial quark, right? Or in this language, it will be how much of the P plus is lost to radiation. And I'm taking an approximation in which I'm not going to be sensitive to that. So, but the energy loss is really the K plus, and in this kind of limit, I'm not going to see the energy loss as the difference between initial and final energy, because those are both infinite in this case. I'm going to see the energy loss as the energy taken by the emitted loop. Okay. So in that case, what I was saying here, I end up with a situation in which now I have here, I start with a P plus. At the end here, I have a Q plus, which is roughly the same as P plus, but now I emitted a gluon, which has a K curve and a K plus. I'm not going to keep track of the transverse momentum of this line. So effectively this line, what will happen with this line is that I will have a transverse position, I will call expert, which is going to be kept constant. So because of this. So the expert is still the same at the end. And I will have Wilson lines. I will have these Wilson lines on this leg. If I call this x1 plus, and this u, and I have put this is let me put some final coordinate x2 plus here at the end. There's some x0 plus here at the end. So this leg is going to be on Wilson line like this. Evaluated at x plus the same here. I have a Wilson line. And this one is this one will give me a propagator and a joint propagator. These ones are fundamental. This I'm writing in momentum space. A1 per. Okay. So, of course, I should be more careful and I should write the whole thing, take the limits carefully to show that that's what we get. But I don't have time for that. So, and then the vertex, we said that it was the combination that appeared there was something like this. There's ones here. But if I take that Z is, I'm taking Z equal to zero, Z going to 0. So really, this in this combination, the Q drops out and I'm left only with the K. So which means that this vector, this vertex here gives me a factor of K1 per. Okay. Now, in practice, what is here at the level of the amplitude, of course, it's linear on this, which means that I have a transverse index attached to this, and that transverse index will be contracted with the polarization vector, the transverse polarization vector that we have. Okay. Now. What we really want to do is to take the square of this. Right, because those are the ingredients that enter in the amplitude. So let me write it like this. I know that this amplitude has a bunch of ingredients. So I can write first the fork line or fundamental line. That's on X. And here the vertex, I will have on color matrix. TA. And I will have the factor of K1 per. And which goes contracted with some polarization vector, some kind of polarization vector. Then we have the other version line. And I will also have the adjoint propagator, which now has, I'm going to write explicitly a color indices, which are adjoint color indices. Okay, and it is important that the index here, one of the indices here contrasts with the index of the color matrix. Okay, just this and that color matrix is right there. Of course, there are a bunch of factors that I'm not writing explicitly. I apologize for that. I'm going to get to what happens if I square this. Of course, I should have written here that there are a bunch of integrations, right? There's an integration over x1 plus, there's an integration over a1 pair. So, when I do this, I have integrations over sorry. I'm going to write this. Let me draw the diagram before I write it. So we're thinking about this sort of process where now if I square it, I have amplitude and conjugate amplitude. Where now, of course, the momenta at the edges, all my variables at the edges, like this x, for example, this x pair that I'm using everywhere, I'm assuming that it is rigid and that it is the same everywhere. That doesn't change. But the k pair that I have here is the same k pair that I have here. Also, I have to, I will sum over the color of the final particle, so I'm going to contract the color indices there. But here I had an x1 plus. Now I'm going to have an x1, let me call it x1 prime plus. So this is really bad notation, but I apologize for that. And also this has a k1 pair, which in principle is not necessarily the same as the one here. So these are different. So what we normally do in this sort of calculation is that we reflect this and draw things like put the two diagrams on top of each other. And when we do that, we're left with something that looks like this. Now, I'm not going to put it exactly on top of each other, but I'm going to draw the two part lines very close to say that they're exactly at the same position. And now these two, the position of the vertex is different. And schematically, the way that we do this is that we connect these two color indices are going to be contracted. These color indices will be contracted here. These color indices will be contracted here. So I always have to sum over initial and final colors. Okay. And then we have to take an average over the external field. So if we take an average over the square of this, I have, first I have a bunch of integration. I'm going to take twice the real part of the integration from x0 plus to x2 plus x1 plus the integration over x1 plus to x2 plus x1 prime plus. So I took a specific order, and I'm saying that this vertex is always after this vertex. The vertex in the conjugate is always after the vertex in the amplitude. And that's arbitrary, but the opposite ordering is just the conjugate. Okay, so I just take twice the real part of this. And then because of all them, because I'm contracting all the color indices, that means that I will have a product of a bunch of, so if you look at the quark line, I have a product of a bunch of Wilson lines, which after I take after I sum over initial and final colors, that whole product becomes a trace. So it's we have an average over the trace of so this is what I have there. Now I have to write the part from the conjugate. So I have also now I have a U dagger. And now in the dagger version, let me write this is just convention. I write the variables in the opposite order. Prime. Now I have a T. I cannot use this A. What's a dummy index? So I have to use a different one. And on top of that, I need to put the loon propagator. This was A. Now I have the dagger of the outline, and where now I have the same B but contracted with C. This from x1 prime plus a1 third one plus a third and plus total average. The adjoint representation is real. We know that taking the dagger is just switching the order here of these indices. Okay. And that's what I get. And now we have to discuss what is how you take averages of these fields. Okay, I'm not gonna get very far. I forgot these factors. So we have to sum our polarizations at the end, which means that the whole thing has an extra factor of K1 per divided into K1 prime per.
And you have to change the upper limit of the second integral, right?
Yes,
Yes, because now you have it ordered.
I put it in the bottom.
Ah, okay, I didn't see it. Sorry.
Yeah, you can write it the other way around.
Yes, yeah.
Okay, so this probably deserves a lot more discussion, but the idea of that average is that we have no idea what to do with external field, right? But the interactions I wrote in terms of some field A and never said anything of the A's. So the idea is that before doing the average, I am doing a calculation where I assume that the A is given. And I know how to, if you give me the A, I can write all this. Now, the fact that we do the calculation with a fixed A, then square it, and then we want to take an average over the different A configurations. What that means is that that's what it means that the A that we're considering is classical. We're assuming that that our parton going through the medium is not changing the background field at all. The field is static, is already there, and my particle is not exciting any new modes or anything like that. Okay, and then so what I will do is say the following. So imagine when we were considering this sort of interactions, well, we have in mind that there's this is scattering with some particle or some quasi-particle that is in the medium, and so it does something to that. It can be so whatever this is affected by the interaction, right? So if I'm thinking about this in the amplitude and then in the conjugate amplitude, remember that we always when we calculate processes like this, we have to have the same momentum here and the same moment. The final state is the same for my parton, but the same is true for whatever scatters I have inside, right? So whatever is the final state of this particle should match the final state of this particle, which gives you an idea that these interactions come in pairs always, right? Because I can have either that, or I can have a two-gluon exchange in which the scatter here is left untouched, right? If I have some momentum transfer Q in this direction, but then I have it compensates with a transfers in the opposite direction, and then I could have the interference of that with the term with no interaction is non-zero. Okay, so I have to take into account all those terms. Now, I could imagine that I can have a lot more combinations. I could imagine that I could have a three-gluon exchange compensated by a one-gluon exchange or something like that. But I'm going to do the simple thing and just say, okay, I'm going to have a Gaussian average. And a Gaussian average, I just have, if I take the average of two fields, one at position X and another field at position Y. Now I'm writing the colors explicitly. And I'm going to say this is diagonal. So this has to conserve color. Now I'm going to impose that this is local in the plus component. And then I'm going to say that this is a function that I will call gamma that depends only on the difference of on the difference of the transverse position times some function n that can possibly depend on the longitudinal position. So this is an assumption, right? I'm just saying this is my only non-trivial correlation between the fields. And what I'm saying is that I will only consider this kind of interactions. Either you have interaction in the amplitude that is matched with an interaction in the conjugate amplitude, or you have these two gluon exchanges. There's nothing else is allowed in this particular model. This is in the small x context. This is called the MV model. It's the same assumptions for those that are familiar with that. And then the extra component is that this that I have this interaction that is local in that is local in the plus coordinate, and what that means is that what I'm assuming is that the separation between interactions or the mean free path is larger than the inverse of the Debye mass of my interaction. So if you assume that these interactions are like sort of Coulomb potential or something like that, it's like a screen potential that has some range of interaction. The range of that interaction is smaller than the mean free path. So it's like I have like definite scattering centers. Okay. We can debate how good of an approximation this is, but this is not the time. So the important thing here, so what we, in principle, we can keep this arbitrary and decide later what we want to put there, what's our model for that, depending on some reasonable assumptions. But the issue is that if we assume that these interactions are local in X plus, that allows us to simplify a lot of this sort of computation here, because that means that I can define different regions here, and the averages of the different regions with different particle content do not interfere between. Okay, so before I'm not going to be able to do anything with this. So before we actually go into those averages, I should simplify this a little bit. This is something very similar to a calculation that Tolga did before. Is that, for example, this Wilson line here is this piece here. Okay. And I can write that Wilson line, I can split it into, because that's a property of the Wilson lines, right? You can write it as a product of the Wilson line from here to here and the Wilson line from here to here. And also the Wilson line, the conjugate, the dagger of the Wilson line is the inverse. So because I'm putting everything everywhere, the quark, I always put in the same transverse coordinate, this piece and this piece will cancel out exactly. And the same happens here. This piece and this piece cancel out exactly, which means that that trace that I had there that trace that tray will become is just this line, and the two color matrices, right? So it's something like A times minus 9 from x plus and sorry. Minus 9 from x plus times A as the line from okay. And now this is something that I should have proven, but I didn't. Is that also these propagators, you can slice them up. You can have an integration over A1 on the kitchen of and then this long one is this one. So propagate the jump propagator B have a thing that's different color curve x1 prime plus then for this two should have done that. Okay. Sorry, this was so why did I do that? The reason is that I want to. So what I wrote here is that this line here is just taking this propagator here and splitting it into divided like from here to here, right here to here, and then I can split them average, and I can just take this one together with this one. There are the ones between x1 prime and x2. And this one together with this one. And actually that trace on the top, there's an identity that tells me that that is exactly an adjoint Winslow line. It's like you have a quark on top of a quark in the conjugate is an anti-quark. So a quark on top of an anti-quark either are in a singlet and completely cancel each other or are in an octet and are indistinguishable from a gluon. Those two look like a gluon, which means that this whole thing is goes like twice the real parts of the integration. So now we have two different averages. and one is this trace is then a Wilson line and a joint Wilson line. Which I want to write as on it's an adjoint. And the Wilson line is let me be sure that I have the correct index here. One plus one times the average of the other two. Okay, so at the end, what we need to do is to calculate the average of a propagator with a Wilson line and the average of two propagators. And there's still one little issue is that I have open color indices here. So here I have C and D. The RDA is contracted and the same happens here. B here is contracted and the C and D are not contracted, but what we know is that there's no, because the color, because these correlations don't introduce any additional color. What we're doing is that we're considering in this sort of diagrams, we're looking at interactions like this, or like this, in this place, for example. So I started with two gluons which had the same color, were in a singlet state, and the transfer of color from this to this will not change that, which means that these two gluons are always in a color singlet state. And what that really means is that I can close the indices here and replace these by traces, both here and here. But okay, we're out of time. I'm really sorry that I didn't get anywhere farther than this. So what I want you to take from this is that the whole process is written as the average of two traces. One is the trace of two propagators, which is this piece here. And the other one is the trace of one propagator and one adjoint Wilson line, which is this place here. So this piece is what is this piece in this area is what usually is called momentum broadening, in the sense that it's like you already emitted the gluon both in the amplitude and the conjugate amplitude, and all these additional interactions, what it just do is like a random walk in transverse space, in transverse momentum space, after it has already been emitted. While the other piece has like the dynamics of the interaction. So that piece, which corresponds to this part over here, is usually referred as the emission kernel. And actually you can integrate over the transverse momentum of the final particle. And if you do that, then you're only keeping track of the energy of the emitted particle. If you do that, then the momentum running disappears, and and then you only care about that other piece that is the kernel. So okay, I'm going to stop there, and anyone who wants to know how to continue from there, please come to me after.
There any quick questions, because this room will be used now for a PhD defense, so we have to pick they want to start. The guy is getting nervous. So, is there a question? Or from the audience?
Yes. It's only assignment.
Okay. If there is nothing, then let's thank Fabio again. Okay, we'll come back this afternoon. Thank you very much.